First off, I just want to introduce myself. My name is Chris Wartinger. I'm a business development manager at MackMedical.
As I'm Jim Hicks with Solvay Advanced Polymers, one of the technical service engineers. We provide support for medical industry.
Great. So first off, I just wanted to thank Jim for agreeing to co-present with me. And so with that, we'll get started. So basically, why are we here? We're here to talk about metal to plastic conversion. And basically, metal has been the material of choice for instruments and devices. Oops, looks like I'm... Okay. And what we're seeing is slides moving on their own. Hold on a second. Yeah, do you know how to do that? Yeah. It's advancing on real quick. Metal has been the material of choice, and what we're seeing in the healthcare industry is instruments are trending to plastic. And basically why that's occurring is, one, to lower cost. One of the main reasons for that is the cycle time of the machinery. Machining a metal piece can take minutes, maybe even hours, where a plastic part can be done in seconds. Also, a lot of times people are afraid of the upfront costs in molding, simply because there's so much capital investment in molds and upfront validation and that type of thing. But we've also found that if done correctly, you can minimize these costs. And I had a customer just a couple of years ago or a year ago that had a 200 part number project, and with over a $2 million investment, and they were able to pay that off, the return on asset, in 1 year. The lifespan of their project was close to 10, so they were able to have that savings for 9 years. So even on smaller volume projects, you can lower the cost. And also, as you lower the cost, you tend to move into plastic parts, which then can be used for disposables. And with disposables, you mitigate infection, etc. So basically, how is this possible? With new plastic resins that have been developed, a robust scientific process development, and validation protocol. So some of the steps that we have to having a plastic product. First off is material selection. Now, as Jim will talk about, there's really a wide range of new plastic resins available. We're also going to look at part design, design for manufacturability, maximizing the design for injection molding process. We'll also look at some upfront concerns with mold design. Also process development, which I consider to be one of the most important aspects and often overlooked, and then look at validation. So Jim will take over from here.
Thank you. So one of the issues to deal with is what material to choose for converting a metal application to plastic. Like metal, there's multiple levels of quality or performance in plastics. And so what we're looking at on this pyramid here, or the lower end of the pyramid, is commodity materials like a polyethylene, polypropylene, up to the high performance materials like a PEEK or a polyimide. So when you're looking at metal to plastic conversions, a lot of the materials you're looking at are in the top performance section of the pyramid here. And so some of the issues you want to look for are the materials biocompatible? I mean, that's first off, if it's going to come in contact with the patient, tissue or fluids, It needs biocompatibility, typically ISO 10993. Is the product going to be disposable or reusable? So what is that going to entail on the material? Which sterilization method you're going to use? Gamma for typically disposable applications, to steam autoclave for reusable components. If it is reusable, most of the time you have cleaning and disinfectant issues to deal with. How's the chemical resistance in the material? How is that going to affect part performance? And finally, what is the property retention? For reusable devices, this is pretty critical because the part will have to go through multiple cycles. So looking at the compatibility with sterilization methods, it's one of the first upfront things to deal with. If it's going to be steam autoclave, you're limited to a few polymers in the industry that can provide repeat performance and repeat autoclave. Materials like PEEK and polyphenylsulfone are some of these materials. For other applications, you may only be dealing with single-use devices that only need gamma, so you have more options to look at. But for the really reusable devices, you got to look at heat resistance and hydrolytic stability for the material. So, again, looking at reviewing the end-use requirements of the part, in the environment you're dealing with, if it's single-use or reusable, how does that environment affect the mechanical properties? Is it a part that has to deal with impaction forces or wear behavior? Is the appearance going to change over time with repeated sterilization cycles? How do those repeat cycles deal with critical tolerances for dimensionally tight components? And then looking at how you're going to, can you actually make the part? Can you design the plastic part to be manufactured? And we look at things like mold flow and FEA analysis to determine if the part can perform equivalent to a metal component. So we did a little example of a traditionally metal component like a retractor and say, what would we have to do to make that a plastic part? So we had to make some assumptions on where it's going to be held and anchored and apply a load on the handle until the stainless steel actually fell. That gives us a place to start to then look at if you take a polymer and design it for the same behavior in the polymer as the metal component saw. We had to make design changes, which, in the original metal design, you had a stress of up to 40,000 psi on the plastic part, much too high for the plastic component. So what we did, and this is very typical in metal to plastic conversions, redesigned the part to be appropriate for a plastic material. And so here we put a little more curve into it. We thickened it up a little. We changed the geometry so that when you apply the same load, you get a much lower stress in the part. And in addition, one of the things we find is it has to feel the same. It had to deflect the same amount, because one of the big issues we find is people don't like the give of a plastic component, and so we had to design it to flex about the same amount as the metal component. And with the load that we applied, it flexed about 2 inches as compared to 1.5 with the metal component. So we got it to be fairly equivalent from a performance and a feel standpoint. So at this point, we're going to talk a little bit about getting into Chris's manufacturing side of it, from the contract side, and what things to consider when converting.
Sure. Thank you. Yeah, so we start off with basically with prototyping. Is there a need for a prototype tool? And basically what you're looking at is, are your requirements, do you need a production equivalent part? And if so, chances are you need to prototype. Also, with those parts that you come out of that mold, you can do mechanical testing and have samples for packaging, etc. The other value that you get out of that is early process development. It gives your technicians time to look at the part geometry, do some serious analysis, and really understanding if there's going to be shrink and warpage issues. Once you have that data, when you go into production, you'll know how to make either a part change, part design change, or a change to the tool itself. When you get to the production stage, it's a little bit easier because it's really a numbers game. I mean, it's how many parts do you expect to make and for what length. So you look at your production forecast, and from there you decide, is it going to be a single cavity mold, multi-cavity, etc., and how much money do you need to invest into that number of production. We also look at special considerations for the type of polymer or resin that would be chosen. Is it a high heat type of resin? So you might need to look at special cooling applications, etc. Also, is there some fiberglass or some glass content? You might have some wear areas, etc. So you have to make special considerations for that type of tool. The next thing I wanted to go into is our advanced quality plan. And I can't say how important this aspect of what we're talking about today is in regards for many reasons. But one of the bigger reasons is that if you do a lot of upfront planning, you can really shorten the lifetime or lead time to market for your product. And what I've found over the years of doing this kind of work, that if you get all these things in line, and I'll go through a few of them, as the mold is being built, once the mold arrives, then you have all the upfront work done, and all you're really doing is collecting data. I can't tell you how many times I've been in a project where the mold shows up and we're still bickering about particulars of the quality plan. So with that, number one thing that I like to start off with and make sure the starting point is a customer-controlled 2D print. And from there, all the other things fall in line. From there, you can do a flow chart, a process, FVMA, control plans, etc. And then out of the 19 elements of this quality plan that I have listed here, we're going to next look at element 13, which is the IQ process, and basically molding machine installation qualification. Element 15, which is the OQ, and element 16 being the PQ. So one of the things I wanted to say about the IQ is basically what you're looking at. Does your processor have machinery, equipment that is reliable and repeatable? That's a big, important part of the start of the project, because then what you need to do through the installation progress is demonstrate that your manufacturing equipment is operating to specification. And then next you look at the mold, and the same thing is put in there. Or the mold or the machine itself, is it the correct size for the molding machine? You have the right clamping, tonnage, barrel capacity. Is the mold built to spec? Is the next one within mold inspection. Oftentimes you have to ensure that the mold coming from the mold maker is to the print or to the PO in which you paid for, you signed up for. And then your other concerns are all the other manufacturing machines that are involved in the process. You need to ensure that the secondary equipment, gauges, etc., you can demonstrate that they're running to spec. Operational qualification. This page kind of goes through the key point of this is the process development. And I think that's where a lot of processors tend not to spend a lot of time up front. Because of that, the rest of the work that they do kind of can get fouled up. You really need to understand the mold and the part geometry. And you do that by doing these various studies, a short shot study, in-mold rheology study, gate and seal analysis, and a back pressure study. Once you have these steps completed, and you understand the mold and what it's producing or able to produce, then you can do your design of experiments. And there you define your optimum process window. And at that point, then you just need to challenge that process with high, low, and nominal process challenge runs. All of that information is collected by doing critical to function measurements and a first article inspection. So in the PQ process, now that we basically understand our process, we know what our limitations are, we know how to process the part, we have to demonstrate that we have a stable and dimensionally capable to making those parts. So what we would do is have 3 molding runs at 4 hours each using different resin lots. So what that allows us to do is basically do 3 separate runs showing that we're capable. There we take sample parts as we identify it after each run and measure our CTFs. We retain those FAIs and CTFs, and at that point our results are recorded and approved. So Jim's going to take the next step.
All right, so to wrap it up in the next 2 slides, what we wanted to kind of emphasize is when you're looking at, going from a metal to a plastic material, choose your polymer supplier and the processor early, because one of the key things we have found is being able to work together with companies like Mack is we get a lot of the problems taken care of early in the process, especially when you're looking at what was traditionally a metal component and all the little nuances that might have to be accounted for going to a plastic material. So, with a polymer supplier, do they have the product characterized fully, for flow and mechanical properties? Do they have support in R&D, tech centers globally to help, if you're going to mold it in the US or China or Europe? And from the processor, do they have experience with some of these higher end materials? Materials like the cell phones and the PEEK materials, and newer materials like our XF, they're different, and the processor having experience with those materials is a huge advantage. And do they have the equipment to handle these high-end materials to deal with high temperature processing? And the financial wherewithal to be able to deal with tooling costs and changes in the program and what it's going to take to bring it to production. And finally, just to sum it up with, there's a lot of advanced polymers out there that can now be substituted for metal in applications that you typically would have never expected. It requires some process development, like I said, jointly with the polymer supplier and a good processing company. And with a robust validation, it gives you new options for the traditional medical instruments that, again, we haven't seen before, but they're very promising and show lower costs and better design flexibility that you would not have expected in a plastic component. So I want to thank you all for stopping by. Chris and I both here at the show, we have booths, so please stop by if you have any additional questions. If we have time, we'll take any additional questions now too. Thank you.